containing function, which is the sign distance function that has high values or positive values outside the interface and negative values inside. And at any location here, this value corresponds to the closest distance to the closest point of the interface itself. So this is a 2D representation. I'll just go one dimension back to one dimension, which is a bit easier to explain what is actually going on. So if you have the same example here with the one dimension, and you have kind of our containing function here in red, you have the section that's below 0 here, which we call the inside of our interface, represented by this green line here, and then we have the outside here represented in blue. And then if you want to manipulate this interface here, we can actually do it by manipulating the containing function instead of manipulating the interface directly. And this has a number of nice properties, as I'll show you in a bit. So we can manipulate this interface by manipulating the function. It's just a very simple example of doing this. It's actually the most simple example you can kind of imagine. So it's one dimension. So if you have phi n here, this is your current sign distance function, represented by this function here. Then, this phi n plus 1 is our updated sign distance function in our kind of next time step of our evolution. If you just subtract a value here, for instance 8, and set it equal to 1, this is the example here, then at each location here you subtract 1, meaning that this 0 value becomes minus 1 down here. And if you do this for all the values here, you get something that looks like this. And you can see the net effect is that our segmentation, or our interface here, that actually expands by 1 in all directions. We can also do manipulations in this way using a vector field. For instance, if you wanted to move this region here using this vector field here, very boring one-dimensional vector, in this direction. So we have this vector field. Then we can apply this update rule here. So we have our vector field V. And then you have just the gradient of our sign distance function here. And if we apply this in a position like this, for instance, where we have a gradient 1 here, then we obtain a value down here, where you can see that the net effect is that our segmented region here actually moves along the vector field here. So enough of these kind of toy examples. You can also do this in another way. You can look at it as kind of vectors kind of acting on your interface with velocities. For instance, this would correspond to the A term you saw before, where you just have expansion uniformly in the normal direction of your interface. Then you can act these vector field contributions, and it doesn't have to be uniformly. They can kind of go in all directions, as you'll see in a bit. And then you can also add curvature optimization. So this curvature optimization seeks to kind of smooth out our interface at all times. And it will actually, for instance, in concave regions like this, it will expand your interface, and in the convex regions up here, it will detract your interface. Then if we add all these vector velocities together, you get like a resulting velocity of each point on your interface that then dictates how your interface actually evolves in the next time step. So this could, for instance, if you want to evolve this one using these vectors, it might look something like this, where you then have the new structure or whatever. Yeah. So of course, we want to design these different terms, for instance, the A term you saw before, and also these vector fields. You want to design them from the actual image data, because otherwise it wouldn't make much sense to actually use these to segment things. So we want to, So for instance, the scalar field you saw before, which would be this part here. So this would be the kind of the full level set evolution equation. We can control this by simply the image intensities in the image, where you say that okay, if we have low intensity or high intensity, then we either expand or detract our surface depending on which phase we actually want to segment. We can also use our image to define our vector field V. We can control this by the gradient in the image. We can, for instance, use it as an attractor, where we attract our interface evolution to sharp edges in our image data. And here you can see the entire level set equation, where you might be able to recognize some of these steps or terms we had before. So this would be the normal direction evolution. This would be the evolution by vector field. And this kappa here is just the mean curvature of the interface. And this is actually a penalization for this curvature effect and so forth. And of course, then we have this step t, which is just the time step that we use to evolve our interface spatially. So here you can see kind of an example of how this is going on in 3 dimensions. Should be said shortly. So you can see that we have these initial seed here in the dark regions. And on top here, you can see that it proceeds to expand such that you can actually cross these high intensity areas here in the middle. You can also see that it keeps nice, smooth surfaces at all times because of this curvature penalization. So here's just another example of another segmentation done on a LSC sample. The one I showed you was actually a set sample. So just to sum up some of these advantages of the level set method is that it forms these coherent structures such that you don't get these, for instance, single pixels or voxels spuriously distributed in, for instance, ratio segmentation. We have these smooth surfaces that are actually evident at each iteration in the segmentation due to our curvature penalization. And we can actually extract from this sign distance function at a later time, we can actually extract the precise interface locations with sub-voxel positions, so we're not really bound to have boundaries that lie directly between voxels. And then finally, we can actually scale the complexity of this level set method up and down depending on how challenging our data is to segment. So that was about segmentation. Now I'll move on about how to actually extract measurements from these segmentations using these sign distance functions. So this section here will be about two-phase boundaries and also interface areas between different phases in the structures. So just to actually sum up what it is we're trying to do and how our data actually looks at the moment. So we have segmented 2 of our 3 phases in our microstructure using these sign distance functions represented by these 2 blobs here, one segmentation here and one segmentation here. And then we define the 3rd phase here as everything that's outside or not segmented in these 2 regions. And of course, what to do is they want to characterize or be able to measure, for instance, the area of these 2-phase boundaries in our structures, and also the 3-phase boundaries. Of course, these are only points in 2 dimensions, but in 3 dimensions they're actually connected curved loops that meet up. So how to actually obtain or make a polygonization from these sign distance functions? So the technique I'll be using here is that in order to get these measurements of surface area and 3-phase boundaries, I do a complete polygonization of all the interfaces in the structures, all the 2-phase boundaries between any specific 2 phases. So if we have this initial segmentation here on a grid of voxels, then a very naive first voxel segmentation might look something like this. And then what we simply do in the start is to just place polygons on the side of these voxels. So this gives us the correct topology of our interfaces, but of course this interface boundary here is not very suited for conducting measurements on because it's of course very blocky. So we want to smooth out our interface so that we can obtain some much more accurate interface and 2-phase boundary estimates. So what we do is that we can then refine the surface based on these sign distance functions that we have, where we can actually extract the precise sub-voxel position location of the interfaces. So for instance, if we have an initial polygonization that looks like this, just line segments here in 2 dimension, and we have kind of the true interface that we would like to approximate with these polygons, then we can sample the sign distance function at these vertices or polygons here, because these locations actually contain the distance to the sign distance function. And also at this location, we we can estimate kind of